Okay, so here we are going to walk through some practice problems using the Hardy-Weinberg equation. And this is from a worksheet called Hardy-Weinberg Equilibrium. And I'm probably going to call it Hardy-Weinberg Equilibrium Tutorial and Practice Questions, maybe. All right, we'll see. Okay, I'm going to share my screen. And okay, we are here. Oh, are we? Nope, wrong thing. Hold, please. Let's try this. Okay, so this is the worksheet that we are going to be working. Oh, why is my iPad being a pain in the tush? Okay, this is the what the worksheet is that we're going to work on. This does a really good job of explaining the Hardy-Weinberg equilibrium and working through these practice questions. And they're shown here as like example 1A, 1B, 2, and 2B. And we're just going to work through those. Okay, so example 1 has a population of cats that are either black or white, and the black allele is dominant to the white allele with complete dominance, so normal Mendelian genetics. So given a population of 1,000 cats, we have 840 black cats, and we have 160 white cats for a total of 1,000 total cats. All right. And so I just want to remind you that if we kind of do a key like we were doing with genetics, that black, since it's dominant, can either be homozygous dominant or a het, but the white are always going to be this recessive. And this is kind of one of the keys to doing the Hardy-Weinberg equation is usually a focus on the recessive allele, all right? Or the homozygous recessive. All right. So given a population of 1,000 cats, determine the allele frequency. So we're going to be looking for the allele frequencies. We're going to be looking for the frequency of genotypes, and we're looking for the number of individuals. All right, so I'm going to kind of call this A, B, and C so we can walk through this. So for part A, we are going to need to calculate allele frequencies. Allele frequencies. And when I mean allele frequencies, I mean how often do you see the big B, which is otherwise called the P, and how often do we see the little b, which is referred to as Q, all right? So sorry, I'm gonna change my iPad orientation here so you can see a little bit better. All right. Okay, so the first thing I'm going to do is, again, I'm going to focus on these white cats up here because I know those white cats are going to respond or going to correspond to this little b, which is the homozygous recessive genotype, right? So I'm going to take 160 cats over the total, and that is going to give me the frequency of homozygous recessive. And that is also referred to as kind of little b, but that is also, if you recognize that, Q squared, all right? So if we do that math out, we have 0.16 is going to be equal to Q squared. From that allows me to very easily find the frequency of Q, right? Which is 0.4. So now I know the allele frequency for Q, or the little allele, is 0.4. And if you remember, P plus Q is always 1. So 1 minus 0.4 is going to be 0.6. So P is equal to 0.6. So that's calculating allele frequencies. For B here, we are going to calculate genotype frequencies. All right, so first allele frequencies, now we're going to focus on genotype frequencies. And once you have your allele frequencies, calculating the genotype frequency is quite easy. All right, so we know, oh, iPad's doing something funky. There we go. All right, so we know that homozygous dominant is referred to as the P squared. So all we have to do is take our P and square it. So that would be 0.36. For a heterozygous, we know it's 2PQ. So it's 2 times 0.4 times 0.6 to give us 0.48. And then our homozygous recessive is going to be Q squared, which we've already calculated, but I want to just make sure that everything is working. And we get our 1.6. So these are our genotype frequencies, right? And just so you know that we can double check our work by doing the following, by plugging into the Hardy-Weinberg equation, right? So remember the Hardy-Weinberg equation is P squared plus 2PQ plus Q squared is equal to 1. So if we take 0.36 plus 0.48 plus 0.16, and we get our 1. So that all seems to check out. All right, now part C, we're supposed to calculate numbers of individuals, right? And to calculate numbers of individuals, we are going to use these frequencies that we figured out from our genotype frequencies, and we are going to then multiply them by the total number. So the number of homozygous dominant is going to be 0.36 times our 1000 to give us 360. The number of hets is going to be 0.48 times 1000. And our number of homozygous recessive is going to be 0.16 times 1000. And we can then just double check that, 360, 480, and 160 gives us our 1000. All right. So that's the way that we're going to do that in example 1. So now in example 1b, it says recall the previous generation had frequencies of P is 0.6 and Q is 0.4, and we calculated that above. The next generation of cats has a total of 800 cats. We have 672 black cats, and we have 128 white cats for a total of 800. We are now asking, is this population in Hardy-Weinberg equilibrium? So the first thing we want to do here is then calculate allele frequencies again. All right. So when we're going to be doing these calculating of allele frequencies, we're going to do something very similar. We're going to take the white ones, which are our homozygous recessive, and we're going to put that over the total. And remember, that is going to be equal to homozygous recessive, which is the same as our Q squared. So when we calculate that out, we get that it's 0.16 is going to be equal to Q squared. And if you get that out, then we're going to see that Q is 0.4. Remember, we can calculate P by 1 minus that. So P is going to be equal to 0.6. And if you recall here, these numbers here are the same as the previous generation. So that means these that this is in fact, so this population is in Hardy-Weinberg equilibrium and had no change in allele frequencies. All right. Okay, so hopefully that makes sense. We're going to work out one other kind of practice problem, which I have shown here. This is also from the same worksheet. So let me modify this. Okay, so here we are looking at the beak color of finches and that are complete dominant, so normal Mendelian genetics, where black beaks are dominant over yellow beaks. And it tells us the genotype numbers. So we have 210. Actually, I'm going to redo that. I'm going to put homozygous dominant is 210. that's going to be a black beak, which is dominant. We have heterozygotes, which are 245 individuals. That's also going to be black beaked. And then we have our homozygous recessive, which is 45, and those are going to be yellow beaked. And that's going to be a total of 210, 245, and 45, a total of 500 finches. Right? So the question is asking, find the frequency of the dominant and recessive alleles. So that again means P and Q, and the frequency of our genotypes. So that's going to be P squared, 2PQ, and Q squared. So again, we're always going to start with our homozygous recessive, right? So first thing I'm going to do is calculate our allele frequencies. So I'm going to do that again by starting with my homozygous recessive alleles. And so we know the genotype of little d is the same as saying Q squared. So when we calculate that, we get 0.09 is Q squared. When we do the square root, Q is going to be equal to 0.3. Then to find P, we can see, remember, Q plus P is equal to 1. So 1 minus 0.3 is going to be 0.7. So P is going to be 0.7. All right. So those are our allele frequencies. So now we are going to calculate our genotype frequencies. So we know that homozygous dominant is the same as P squared. So we can take 0.7 and square it to give us 0.49. Our heterozygotes are 2PQ. So that's going to be 2 times 0.3 times 0.7, which is going to give us 0.42. And our homozygous recessive, which we've already solved for, but it's always nice to just check our work, is 0.3 squared. So that is going to give us our hold on here. .3 squared. Oh yeah, sorry, 0.09. Just wanted to double check. I have it wrong in my notes here, which is silly. 0.09. Okay, so and we can always go back and check. So 0.49 plus 0.42 plus 0.09 is in fact 1. So you can check in our P squared plus 2PQ plus Q squared equals 1. And that in fact checks out. So 0.49 plus 0.42 plus 0.09 does in fact equal 1. All right, so the next generation of finches has a population of 400, and there are 336 black beaked, and we have 64 yellow beaks, right, for a total of 400. So again, we're always going to use our homozygous or our recessive phenotype. So we know that 64 over 400 is going to be our homozygous recessive phenotype, which would be Q squared. And so we can go ahead and figure out that math, and that will give us 0.16 is going to be Q squared. If we square that, or if we figure out that, if we do the square root of that, we have Q is equal to 0.4. And P is going to be equal to 1 minus 0.4. So P is going to be equal to 0.6. And so our question is this population in Hardy-Weinberg equilibrium? So we need to compare our previous, so generation 1 had P equals 0.7 and Q is 0.3. And our new generation has our P and Q as 0.4 and 0.6. So this population is not in Hardy-Weinberg equilibrium because allele frequencies changed. All right, so those are just some good practice questions. I want to point out that the end of this worksheet has a lot of practice questions, which are really good. So you should definitely try try those out, and I can post a key. Oh, the solutions are right there. So the key is already attached to this. All right, chip, chip, cheerio. Bye.